Hi everyone. So we're going to be looking at Newton's second law in rotation. You'll have noticed by now that everything that we did in linear motion has an equivalent in rotational motion. This is still the case. Newton's second law in rotation. Say we have this object. It can be anything. In this case, we have a rod and a bob. So just imagine a rod and a mass fixed at one point. It's a rigid object, much like this marker. If a force is being applied some distance from an axis of rotation, from a pivot point, it will create a torque. The object will rotate. Now, how exactly do we find that? Newton's second law. Say we have this here. We have a force that's being applied on the bob right here at the very end of the rod. Assume also that the bob itself is very massive but very, very small, so it's essentially a point, right? It doesn't have a big volume. What we'll have is a torque we can find by taking R cross F, and we find what it is. How do we relate that to the acceleration? Well, Newton's second law in linear motion said this. The sum of the forces, or the net force acting on an object, is equal to the mass times the acceleration of the object. That assumed that all of the forces were going through the center of mass and the object was accelerating uniformly. In rotational motion, it's written like this. The sum of the torques is equal to the moment of inertia times the angular acceleration. So what we have here is that the net force or torque acting on the object will be equal to the inertial property of the object, mass or moment of inertia, times the acceleration of the object, either linear or angular acceleration. This is Newton's second law in rotation. It's a vector equation, which means that, as always, we'll tend to ignore the direction of the vectors and just worry about the magnitudes and look at the diagram to see what is the sign of those torques. For most of our cases, we'll again consider all of the forces to be applied in the xy plane, and also all of the vectors are the position vector where those forces are being applied to be in the xy plane. That means that by the law of the cross product, the torques will always be along the z direction, plus or minus. So all of the torques kind of are one-dimensional in nature. All that we can do then is just add a plus sign in front of a torque that causes a positive rotation and a negative sign in front of a torque that causes a negative rotation. You can see the examples in the notes for how exactly to apply that. And yeah, so that's it about torques. Now let's move on to equilibrium.